Alright, so having seen the first fundamental theorem of calculus and having proved it, next we are going to see an example. But before we do so, let us once more see the statement of the previous theorem, that is the first theorem. What it said is this: you have a function f which is a real valued function on a closed bounded interval. This means that a and b are real numbers and also a is less than b, and we are given that this function is Riemann integrable. Okay, so we have this function, and using this we then define another function f. Capital F, and the definition of capital F is this. Then what was the conclusion? The conclusion is that capital F is continuous. On this entire interval, it's continuous. At every point of this interval, capital F is continuous. And additionally, if this is a point, any point in this interval where small f is continuous, then capital F is differentiable at that point. Differentiable at x naught, and the derivative of capital F at x naught is the value of small f at x naught. So this was the statement of the first fundamental theorem. Alright, so now let us recall in this example something that we saw earlier when we were studying monotonic functions, and this we saw in exercise 985. In exercise 985, we saw a monotonic function f from R to R, that is discontinuous on the set of rational numbers and continuous on the set of irrational numbers. Okay, so this strange function we actually constructed, and it was an exercise. There we proved this fact. Now, because the function is monotonic, in fact, if you remember, it is strictly monotonically increasing. Because it is monotonic, it is integrable. I mean, if you restrict the function on a closed bounded interval, say 0, 1, and that of course follows from proposition 11.6.1, from that section where we discussed integrability of monotonic functions. So by proposition, let me write simply prop 11.6.1, f is Riemann integrable on 0 comma 1. Okay, so f is Riemann integrable on 0 comma 1. Just like here in the first theorem, we have a Riemann integrable function. Now, if for this particular f, I mean its restriction on 0 comma 1, for that f, if you similarly define capital F, then capital F is continuous. Okay. Additionally, the places where small f is continuous, capital F will be differentiable at those places. Our small f is continuous at every irrational number. So, the capital F that you will get from this function will be differentiable at every irrational number. And at every irrational number, its derivative will be equal to the value of small f at that number. But additionally, something else is also true, which doesn't follow from this first theorem, which is that capital F for our specific small f here is simultaneously not differentiable at any rational number. And this is what we will prove in the first exercise of this section. That means exercise 11.9.1. You just take a moment to think of this capital F. It's a very strange function because capital F now is coming from small f, which itself is quite strange, that it's continuous at every irrational but discontinuous at every rational. So, capital F also inherits that strangeness by being differentiable only at irrational numbers. To justify this statement, though, we need to show in this exercise that it's not differentiable at any rational also. We will do that when we solve this exercise. Alright. Now, let us take a moment to see just roughly what the first theorem says. What is small f? Small f is a given function, and capital F is, in a sense, the integral of small f. And differentiating capital F, we get small f back. In other words, if we write this thing very vaguely, then this is how we can write a very vague equation which simply conveys this fact that differentiating an integral gives us the original function back. This is our capital F. I mean, roughly it looks like this. Oh, sorry. This is what capital F is. Okay. Differentiating capital F gives us small f back. That means derivative of integral gives us the function back. Now, the second fundamental theorem does its opposite. In it, we are going to integrate a derivative and get the original function back. But before we state the second fundamental theorem, we need the notion of antiderivatives. Okay, there is a distinction between antiderivatives and integrals. Now we are going to see the definition. So let us first define antiderivative and then we can state the second fundamental theorem. So this is the next item. It will be definition 11.9.3 because this is 2. Alright, let small f from I to R be a function where I is a bounded interval in R. There is virtually no restriction on small f. Small f is just a function. The only restriction is that its domain is an interval. It's a bounded interval. Being a bounded interval, I can be closed, or the two types of half open intervals or open. Okay, so those possibilities are there. F, we are not saying that f is integrable or differentiable, no, nothing. F is just simply f. We call a function f. Do not think of this f as that f. Okay, so this is something new, which also has I as its domain and is also real valued, and antiderivative of small f if capital F is differentiable on I. There is a restriction on capital F, that it is differentiable on I. And the derivative of capital F at x is equal to the value of small f at x. It's like the capital F we have in the first fundamental theorem statement, but I said that this is something new because this f is just some f which satisfies this condition. We are not saying that this f is related to small f via an integral, no, nothing like that. It's just a function which satisfies only the condition that it is differentiable and its derivative on I identically equals small f. If that's true, then we call capital F an antiderivative of small f. Do you see this indefinite article n? That means a function f may have more than one antiderivative. Actually, that's the case. Okay. Or it may have no antiderivative at all. That is also possible. Now we can state the second fundamental theorem. So here it goes. This obviously will be 4. Of calculus. Okay. The statement is quite simple. Let small f, this time however we consider a closed interval, be a Riemann integrable function where a and b are two real numbers such that a is less than b. That means this is a bounded closed interval in R. Okay. Let, so that is given to us, something else is also given. let capital F from a comma b to r be an antiderivative of small f. That means small f has an antiderivative, at least one antiderivative, and capital F is one such. Then the integral of small f over its domain is capital F of b minus capital F of a. This is the thing we did in school calculus when we are taught integration for the first time. What we do, before we see the proof, let us just simply see one situation which we have seen many times. Say you have something like this. Let us consider an absolutely simple integral, definite integral. How do you calculate this? Forget about Riemann integration. If you forget everything, you just do it school style. What do? You find first an antiderivative of the integrand x. And what is that antiderivative? It is a function whose derivative is x. Now, if you think of the power rule for differentiation, from what do you get x? X square. But if you differentiate x square, you do not simply get x, you get 2x. To adjust that 2, you write x square divided by 2. Because if you differentiate this with respect to x, you get 2x divided by 2, and that is just x. So this x square over 2 is an antiderivative of x. If we did not have these limits, if it was an indefinite integral, then you add a c, because as the definition says, an antiderivative. There may be multiple antiderivatives of a given function. Actually, all of them look like this. They only differ from each other by some constant. That is why we write plus c. This is the set or collection of all antiderivatives. In fact, that's what indefinite integral is. It is simply antiderivative. So if you want to find all antiderivatives, you write plus c, so that everything is taken into account. Now you can ask me, why is it that all antiderivatives can be found by simply adding plus c? How do you know? In fact, that's coming. Okay, there is a result at the end of this section. But definite integral is something else. In definite integral, what you do after finding the antiderivative, you either put a vertical bar or you place that antiderivative within square brackets, and then you write these limits. Or somewhat more simply, you simply write 0 and 1, and then what you do, you first substitute the upper limit, and then minus, then you substitute the lower limit. Then you calculate the value, and that is the value of the integral. That's how we are taught integration in school. In fact, this is the only thing we know about integration in school. However, now we are seeing something else. No? Now the way we are learning about integration, Riemann integral, that involves upper sums, lower sums, upper integral, lower integral, which in the beginning has apparently nothing to do with antiderivatives. It in fact has nothing to do with derivatives at all. We just find upper integral and lower integral. If they are equal, then the function is called integrable and the common value is the value of the integral. That's actually what integration is. But the thing we are taught in school is something else. I mean, it looks like something else. Instead of finding upper and lower integral, you suddenly find antiderivative and calculate the integral value like this. The fact that these two things actually give us the same thing is justified by this result. That is why what we are taught in school is in fact not the definition of integral, it's actually a result, the second fundamental theorem of calculus. Now the question is, why are we taught this in school? Why do we not tell students that integral is the common value of upper and lower Riemann integrals? If they are equal, then the function is integrable. If they are not equal, then it's not integrable. The problem with that is that in school, we do not know that the system of real numbers has the least upper bound property. Without least upper bound property, you cannot define upper Riemann integral, lower Riemann integral, because they are greatest lower bounds and least upper bounds. These things you cannot talk about in school. And that is why instead what is done is only those kind of functions are taken as integrals for which antiderivatives exist, and then integration becomes easy because of the second fundamental theorem. There are, fortunately or unfortunately, some functions which are integrable but for which there is no antiderivative. So to integrate those functions you cannot use this school method, but they are not shown in school. But fortunately, most of the functions that we encounter even in applications do have antiderivatives. Okay, I mean I am talking about simple applications. But every now and then you will see that there are some integrals which cannot be calculated like this. Okay, so school integration happens because of this theorem. Now let's prove the theorem. We will start the proof by considering any partition of this interval. Let P be any partition of our interval a comma b. All right. Then what we do? Then we recall the what is that thing called? Additivity of alpha lengths. You remember when we studied Riemann-Stieltjes integral, in the beginning itself we generalized the notion of the length of an interval, of a bounded interval, to its alpha length. If you have an interval with endpoints a and b, say an interval like this, say this interval, then for any function alpha in whose domain this is a subset, you can define the alpha length as alpha of b minus alpha of a. Whereas what is the ordinary length? The ordinary length is simply b minus a. So that's the special case where alpha is the identity function. Alright. Now what we are going to do, we will calculate the f length of this interval, where we are considering the function f in place of alpha. You may have a confusion that we are not given that f is monotonically increasing. That's not a problem. We just want the f length of this interval. The original definition of alpha length does not assume that alpha is monotonically increasing, which is why sometimes alpha lengths become negative. We have already seen one example of that. So we can calculate the f length of this interval, and the additive property of alpha length says that if you take a partition of your interval, then the alpha length of the interval is equal to the sum of the alpha lengths of the subintervals in that partition. This we are going to use. So let's see what we get. And that property that is coming from which theorem, you need to mention that also. It's not a theorem, it's a lemma. By lemma 11.8.4, the f length of this interval is f of b by the definition of alpha length, okay, minus f of a. So this is the f length. So do you see that we are already getting fb minus fa? And this is why we need Riemann-Stieltjes integral, because it gives us many things. But by this lemma, this is summation f j, where j varies over the partition, because P may have the empty set as one of its elements, and by definition the f length of the empty set is 0. So we can not consider the empty set, that is j belongs to P and j is different from the empty set, because not considering it does not affect anything. Alright. Now, let j be any element in P such that j is not the empty set. Even then, j can be a singleton set. In that way also j can be degenerate. That is possible if j is singleton or degenerate. Anything you can write has the same meaning. Let me write degenerate. Then f of j is 0, because alpha length of any degenerate interval by definition is 0, just like ordinary length. And note that this is also equal to times the length of j, that is supremum of the f values as x varies over this interval. Means in this case it's only one point, so you will just have only one value, which is f of x, times the length of j, because j is degenerate, both alpha length and length are 0, so you are getting equality. But if j is non-degenerate, if j is non-degenerate, then it's of the form closed interval C comma D, or closed open interval, or open closed interval, or open interval for some real numbers C and D where C is less than D. In this case, what is f of j? F of j is f of D minus f of C, again by the definition of alpha length. I mean, in this case, f length, capital F length. So this is f of j. Okay. However, well, I should have written this first. F of j by definition is fd minus f of c. Okay. But we know something about this capital F, namely that capital F is differentiable. Differentiable where capital F has this closed interval as its domain, right? And this interval, I mean whatever it is, in whatever form our j is a subinterval, it's a subset of this. So if capital F is differentiable, right, then it will also be differentiable on the closed interval C comma D. Our j actually need not be this. J may be this or this or this. Regardless of the situation, this closed interval is always contained in this subset. Why? Because J is a subset of this and this is a closed set. So the boundary points, which are limit points, will belong to this. C and D are always there inside this because of that fact. So if you now restrict f on C comma D, then there f is differentiable. At the boundary points it has one-sided derivative, but it's differentiable. As a result, capital F is continuous on C comma D as well. Capital F is continuous on closed interval. Differentiability you can consider on the open interval. So does that remind you of something? The mean value theorem. By the mean value theorem, we will then have this. Fd minus Fc will be capital F prime at some point times D minus C for some E belonging to the open interval C comma D. This is happening because of the mean value theorem, which we can apply because capital F is differentiable. And that's why in place of Fd minus Fc, now we can write this. So now we can continue our calculation. F prime of E times D minus C, but we need to write also for some E belonging to C comma D. In brackets we write by the mean value theorem. Mean value theorem is such a powerful tool, it gives us many things. Later we will see that it also gives us Taylor series, Maclaurin series, those things. So, or hence, so what are we getting? Fj, which is fd minus fc, this is f prime of e. However, what is f prime? Because capital F is the antiderivative of small f, this is simply f of e times d minus c. Now f of e, of course, is less than or equal to the supremum of all the f values as x varies over j. Note that we are only considering e inside this open interval, but no matter what j is, whether j is this or this or this or this, the open interval is always contained inside j. So that is why f of e will be less than or equal to the supremum of f of x as x varies over j. And what is d minus c? D minus c, no matter what j is the ordinary length of j. So you see that in the special case where j is degenerate, you have equality of f of j and this quantity, but in general you have inequality. So we can write thus: in any case, f of j is less than or equal to this. Do you see why we carefully avoided the case where j is empty set? I mean, it was not simply done because it can be done there when we were considering f of the entire interval economy. It is because if j is empty, the set we are considering here of the f values is also empty, but then supremum by definition will become minus infinity. We do not want that. That is why. So now we go back to those sums. Hence, fb minus fa, which we calculated to be this as j varies over t, but j is not empty. So this now becomes less than or equal to summation If you want to separate this supremum, you can use brackets. But what is this? This is something we know, okay. And if you recall, this is nothing but the upper Riemann sum of f for the partition P. So we have shown that no matter what partition P of our closed interval a, b we choose, this fb minus fa is always less than or equal to the upper Riemann sum for that partition. So actually for every partition, this will be the case. Similarly, we can also prove that the lower Riemann sum of f for the partition P is itself less than or equal to, this one is greater than or equal to this one will be less than or equal to f of b minus f of a. So for the set of all lower sums, as you change the partition, this is an upper bound, whereas for the set of all upper sums, this is a lower bound, and that is why what is the least upper bound of the set of all lower sums? By a previous result, that is the lower Riemann integral of f. Least upper bound. This is some upper bound, this is the least upper bound. So this will be less than or equal to f of b minus f of a. Similarly, because this is a lower bound for the set of all upper sums, the greatest lower bound of the set of all upper sums will be greater than or equal to this quantity, because this is just one lower bound and the greatest lower bound is the greatest of all lower bounds, and so we simultaneously get that which is less than or equal to the upper Riemann integral of f over a comma b. But f is Riemann integrable so the lower integral is equal to the upper integral, which is simply the integral of f. Thus, the integral of f is less than or equal to f of b minus f of a, which is less than or equal to the integral of f. And that's why this is equal to this. And that's the proof of the theorem. Now you know why that school technique works. The actual reason behind the school technique. So if you are lucky enough that your function small f has an antiderivative, then calculating integral can be done school style and it becomes quite easy. Next comes the question of what type of functions have antiderivatives and which ones don't have. There is a particular situation in which functions do have antiderivative guaranteed by the first fundamental theorem of calculus. Consider a function like this. Which has two things on it, that it is continuous and Riemann integrable. By now we know very well that continuity is not a necessary condition for integrability. We have already seen many discontinuous functions which are integrable. For example, a monotonic function is always integrable. It need not be continuous. In fact, discontinuous but piecewise continuous functions are also integrable. So for such functions, integrals exist. We can calculate those integrals. But if the function is continuous also, fine, then also it's integrable. Alright, now for this function, if one defines capital F like this, like how we have capital F in the first fundamental theorem. What does the first fundamental theorem say? I mean, what is its conclusion? The first part of the conclusion is that capital F is continuous. And what is the second part? The second part says that the points where small f is continuous, there capital F is differentiable. But if here small f is continuous at every point, so capital F accordingly will also be differentiable at every point. That means capital F is differentiable on this. And additionally, what is true? Namely, that the derivative of capital F at x is equal to the value of small f at x for all x where small f is continuous. That means now it's for all x in this interval. But then what is capital F? Capital F is then an antiderivative Now you recall your school integrands, sin x, cos x and other integrands, other functions that we normally take, any polynomial function, say x cube plus x square, all these are continuous functions. I mean, wherever they are defined, there are some functions, for example, the tangent function is not defined at odd integral multiples of pi divided by 2. I mean, if you avoid those points, elsewhere the functions are not just defined, they are continuous. Now you think of your school integrals, most of the functions that you are normally given to integrate are such functions, continuous, and that is why this guarantees that they have antiderivatives. You know that from this theorem. Now it's a different matter that you have to spend some energy to find those antiderivatives. That's what school integration involves. That is where it's a little tricky. You have to apply integration by parts, partial fraction, trigonometric substitution. So everything then depends on finding out those antiderivatives. But the guarantee comes from here that at least one antiderivative exists. So for continuous functions, the integration is school integration. You do not have to think of Riemann integral or anything. But for discontinuous functions, it's a more delicate matter and it's a graduate level topic. Whether such functions also can be integrated, do they have antiderivatives? If so, you can apply this theorem, otherwise it cannot. Okay, so that is a higher level topic. And also the author says that not every function which has an antiderivative is Riemann integrable. That is also there. For example, he gives us an example. So what does professor say? He says that it's not necessary that if a function has antiderivative, then it should also be integrable. I mean, in a frenzy to find antiderivatives, we may simply just pick one function and somehow find an antiderivative and then blindly we just go for integrating it. No, that's not, I mean, integrability is, it does not come from existence of antiderivative. One such function is given here. The function is like this, and its definition is partly given. At every non-zero real number within this interval, of course, this is x square times sine of 1 over x cube if x is not equal to 0, and it's defined to be 0 if x is equal to 0. This function is differentiable everywhere. You can already see why it is differentiable at any non-zero real number, because you can apply the algebra of derivatives. No. Is 1 divided by x cube differentiable when at a point where x is non-zero? Yes, because it's a rational function. So if you apply the quotient rule for differentiation, that itself tells us that 1 over x cube is differentiable. But we do not simply have 1 over x cube, we have sine of that. The sine function is differentiable throughout the real line. So the composition of these two differentiable functions by the chain rule is also differentiable at every non-zero real number, and x square being a polynomial is also differentiable. In fact, its derivative is just 2x. So the product of these two differentiable functions at a non-zero real number is also differentiable. So differentiability of capital F when x is not equal to 0 is already there. I mean, it follows from the properties of derivatives. At 0, however, you have to check carefully. What is this? You have to apply the definition. H tends to 0, f of h minus f of 0 divided by h. That's what derivative is, right? This limit. Now f of 0 by definition is 0, so that part is gone. And I should have actually, I mean, if you follow the notation that tau follows, you should also write that h varies over this, or okay, I mean this domain, minus 1 comma 1. So we have that thing here, okay. Now what is f of h? So h is non-zero. H is coming from this interval, but h is non-zero. So you can use this part of the definition. That gives you this. Now one h gets cancelled, so the limit you have to calculate of the function is, I mean the function is h sine 1 over h cube, and this limit is 0. You can apply the squeeze test to see why. That's because the absolute value of sine 1 over h cube is less than or equal to 1, so that's why. That means this is 0. So f is also differentiable at 0 and the derivative is 0. Now if you consider the derivative is also a function, no? If you consider the derivative, how will it look? We have just now calculated that at 0 the derivative is 0, and if x is non-zero, what is the derivative there? You apply the differentiation rules. We have to apply the product rule, so you differentiate x square plus, x square first, you keep the sine term as it is, and then use the chain rule to differentiate the sine term, and you keep the x square term intact. So the chain rule will give us what? X square differentiating sine will give us cos times differentiating 1 over x cube gives us minus 3 divided by x to the power 4. Minus 3 over x square cos 1 over x cube. Note carefully that this is for those x that are non-zero, and on this interval this function is not bounded. The closer you go to 0, the larger the values become numerically. I mean, they go down as well as up. The amplitude just simply keeps on increasing. So this is unbounded. Although it's inside a closed interval, but there itself it's unbounded. So no question of differentiability. If you are very happy and ecstatic about being able to find an antiderivative of, say, your function itself is f prime. Okay, so this is the function you started with, and you find an antiderivative. This is your antiderivative. Whose derivative is this? And you just blindly go on calculating the integral of this using the second fundamental theorem, using this this function and calculating f of 1, capital F of 1 minus capital F of minus, no. The function you are trying to integrate is unbounded to begin with. So how can it be integrable? I mean, it is not Riemann integrable. If its integral exists in some sense, that will follow some other definition. After this example comes that result where the author tells us that any two antiderivatives of a function differ by a constant, but that we will see in the next video. And there is one more section where we are going to see some other things that also we already know. For example, integration by parts. We are going to prove that result, why it works. It is also something we have used so many times, no, in school. So let me just end the video here itself. Tomorrow is Monday. That means we have, what do we have? Number theory. Okay, so see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.